Design of DC-DC converter bench controlled by an Arduino microcontroller. Abstract. The main purpose of this paper is to design a DC-DC converter bench controlled by an Arduino board. This DC-DC converter bench is dedicated to the teaching of power electronics labs. Several DC-DC converters topologies can be studied. Proteus simulations were carried out for the different structures. Introduction. A power converter circuit manages the flow of electrical energy between a source and a load. Until a few years ago, their primary use was in supplying motors in industrial applications and in electric traction systems. Nowadays, in addition to those fields, they are employed in very wide range of applications including domestic applications, renewable energy systems, FACS, flexible alternating current transmission system, automotive. Innovations in the field of power converters are taking place on several axes: new generation of power semiconductors, more and more new configurations of power converters, the use of digital devices such as microcontrollers, FPGA, field programmable gate arrays, in control circuits. Modern power converters offer a high grade of precision, flexibility, communication capability, reliability to the end user, with smaller sizes. This paper presents the design of DC-DC converter bench controlled by an Arduino card. Experiments and Proteus simulations are carried out for elementary structures of DC-DC converters such as buck-boost converters. A block diagram of the experimental bench is shown in Fig.1. A DC power source, mostly battery, is used to power the DC-DC converter. The pulse needed for switching the semiconductor is generated from the Arduino Uno. The code is written with the open-source Arduino software, IDE. The measurement of the different currents and voltages can be done either by the Arduino card or by an oscilloscope. The type and the values of the components used are as follows. Table I. Components of the control circuit. VEN is the voltage delivered by the PIN7 of the Arduino. VEN is a square wave voltage. The low level is 0V and the high level is 5V. In order to have a square wave voltage with a frequency f equals 1 kHz and a duty cycle d equals 0.6, the following code must be written with the Arduino software, IDE. When VEN is at the low level, 0V, the transistor T is off, open, then VGS VCC equals 15V, for R equals 1K, the voltage across the resistor R can be neglected. When VEN is at the high level, 5V, the transistor T is on, saturated, then VGS 0V. Fig.4 shows a simulation of the control circuit on Proteus. Fig.6, control voltage measured. 3 power circuit. Experiments are carried out for 3 DC-DC converters structures that are buck converter, boost converter, and buck boost converter. The type and the values of the components used are as follows. A buck converter. The buck converter is shown in Fig.7. It operates by periodically opening and closing an electronic switch, MOSFET. It is called a buck converter because the output voltage is less than the input. In practice, the following configuration, Fig.8, is preferred. Its main advantage is the common ground for both control and power circuits. Theoretical waveforms for buck converter are as follows. U, T, and I, T, are output, load, voltage and current. The average of the output voltage U, T, is given by equals 1. D is the duty cycle. B boost converter. The boost converter is shown in Fig.10. It is called a boost converter because the output voltage is larger than the input. In theory, the capacitor C is considered so large that the output voltage U is held constant at equals. The analysis proceeds by examining the inductor voltage, VL, and the switch voltage, VM, for the switch closed and again for the switch open. See buck boost converter. The buck boost converter is shown in Fig.14. The output voltage of the buck boost converter can be either higher or lower than the input voltage. In practice, the following configuration, Fig.15, is preferred. Its main advantage is the common ground for both control and power circuits. In theory, the capacitor C is considered so large that the output voltage U is held constant at equals. The analysis proceeds by examining the inductor voltage, VL, for the switch closed and again for the switch open. When the switch is closed. When the switch is open. Equals dash. 7. Theoretical inductor voltage. For buck-boost converter is as follows. The average inductor voltage must be 0 for periodic operation, then. For simulations and results. In this section, Proteus simulations and real measurements are shown for the three configurations of DC-DC converters. A buck converter. The complete buck converter circuit, control and power, is simulated using the Proteus software. Simulation is carried out for the practical values. The yellow waveform represents the load current and the red waveform represents the load voltage. Practical measurements are in accordance with theory and simulation as shown in Fig.21. B boost converter. The complete boost converter circuit, control and power, is simulated using the Proteus software. Simulation is carried out for the practical values. The yellow waveform represents the switch voltage. And the red waveform represents the load voltage. Since the capacitor C has a finite value, C equals 54F, the output voltage U is not constant, it has a ripple. Practical measurements confirm Proteus simulation as shown in Fig.24. C buck-boost converter. The complete buck-boost converter circuit, control and power, is simulated using the Proteus software. Simulation is carried out for the practical values. The yellow waveform represents the inductor voltage. And the red waveform represents the load voltage. Since the capacitor C has a finite value, C equals 54F, the output voltage U is not constant, it has a ripple. Practical measurements confirm Proteus simulation as shown in Fig.27. V conclusion. In this project, a DC-DC converter bench is designed. This experimental bench is a multi-topology bench. It allows students to study the elementary DC-DC converters that are buck-boost and buck-boost converters. For this DC-DC converter, the pulse needed for switching semiconductor device is generated using the Arduino Uno. Before performing experimental measurements, simulations with the Proteus software are carried out. The simulations results obtained are in accordance with measurements. This project highlights that Arduino offers a simple and efficient way to control power converters.